Buenos dias, hola, everybody. Today we have a speaker all the way from the city of good air, Buenos Aires, Guillermo Cortiñas, Leavitt path algebras and AK theory. The floor is yours, the walls are yours, take it away.
Well, thank you for such a wonderful introduction, and thank you, Piotr, for the invitation to speak.
My pleasure.
Before I forget, let me mention that
Willy,
yes.
Can you kind of, I don't know, take over the screen or something? Because we see very small bit of it.
Yeah.
Oh, wait, is the better view?
Yeah.
Oh, yeah, sorry, speaker. Yeah, okay.
Yeah.
I'm sorry.
I think that this is you who can fix it. I think I will.
Yes, so I did already. Yeah.
Speaker view. You have to put on speaker view.
Yeah, speaker view. Yeah.
Mm-hmm.
You can pin one of the screens, the windows. Okay. So any new result that I mentioned is in my latest paper from this year. So I only have uploaded one paper this year. I mean, I have uploaded a new version of another paper from last year, but the new one is here. The paper is called Classifying Leavitt path algebras up to Involution Preserving Homotopies. Okay, so let me start with a few recollections about Leavitt path algebras, which if you follow, if you've been following Piotr's course, you must be familiar with. So in this talk, a graph is always oriented and consists of two sets, one set of edges and one set of vertices, and an edge is best thought of as a little arrow coming out of its source and ending in its range. Okay, so this is the definition of graph, of oriented graph. And then a finite path is a sequence E1, En, so that for every I, the range of EI is the source of EI plus 1. If this is alpha, then this N is the length of alpha. And if I have a vertex, then I consider it as a path of length 0. Okay? And I write PE for the set of all finite paths. Now, in this set, we have a partially defined operation, which is concatenation. So you have two of these, two finite paths, and if the end of this one, the range of En, coincides with the beginning of the other one, then you can concatenate them. So I want to make a semigroup out of PE, so I add 0, which you may thought of as the finite path, including the empty path. And here we have a product, which is concatenation if this is possible, and 0 otherwise. So this is a semigroup, and this semigroup, the algebra of if you have now a commutative ring, say, or a field, then you can form the semigroup algebra of this PE, and this is what is called the path algebra in terms of, I mean, what people in representation theory of finite dimensional algebras and such call the path algebra. But this is not our path algebra. We first make this into an inverse semigroup by adding an E star for each edge, so that E star F is delta EF, range of E for E and F in E1. Okay? So we come up with an inverse semigroup, and then given this inverse semigroup, you may again, by the way, I should say that concretely SE consists of 0 and all the elements alpha, beta, star, where the range of alpha is equal to the range of beta. Here the star of a path is the product of the stars of the edges and composite in the reverse order. Okay, so then now say L. I always have the ability to pick whichever marker has the less ink. So say L is commutative ring, and then you can form what I will call CE. There is no reference to L in this one, but it is implicit. This is the sum of L alpha beta star, as here. So this is the semigroup algebra. And so a module, a CE module, is the same as a semigroup. So you have an L module M and a semigroup homomorphism. Where here I consider the L linear endomorphisms of M as a semigroup with composition. All right, let me find. Here. Let me get a new marker. Okay. So this is what a module is. Now, if L is a complex numbers, you can, instead of considering just representations in C modules, you can consider representations as bounded operators in Hilbert spaces. And then these representations give you a maximum norm. And when you complete CE with that maximum norm, with respect to that maximum norm, you get what is called, usually called the Teplitz algebra, which is a C-star algebra. Now, the Leavitt path algebra is a quotient of CE. And to tell you what kind of quotient it is, I need to tell you first what a regular vertex is. So the vertex is regular if the number of arrows, of edges it emits, is finite and non-empty. So we write reg E for all the regular vertices. And so we divide this by V minus the sum of E star, for source of V equal to V, such that V is regular. Now, what is an LE module? Well, it's a representation of SE as endomorphisms of some L module that is tight in the sense of Excel. And so you may think of LE as the universal algebra for tight representation. So this condition is equivalent to the condition more generally defined for inverse semigroups by Excel, that the representation be tight. Yeah, and if you, again, when L is C, you may take tight representations as bounded operators in Hilbert spaces, and if you complete with respect to the associated norm, you get, well, I will denote OE, that is the Kunz-Krieger C-star algebra. Okay? All right. So the algebra LE is the subject of this talk. I need to introduce one further piece of notation, which is which are the incidence matrix of a graph and its Bauern-Franks group. So AE is a matrix with integer coefficients indexed by the vertices of E0, but in the rows I only consider regular vertices. And so that its BW coefficient is the number of edges which start in B and end in W. So this is a number, an integer number, a positive or a non-negative integer number, because I've limited myself to be being regular. So if it's regular, it cannot emit infinitely many vertices. Also, it cannot be a sink. So that is, it does have to emit some vertex. So in this matrix, there are no zero rows. Okay. And now I make a terrible abuse of notation and use I not for the identity matrix, but for a matrix, for the matrix which is obtained by the identity matrix of size E0 times the regular vertices, so that EBW is delta BW. Okay, so this matrix lives in the same place as the transpose of this matrix. And now I consider the Bauern-Franks group of E to be the co-kernel of I minus AET. This is the Bauern-Franks group. All right. So if E has finitely many vertices, then you can add the the classes of each of the generators. So the I think of the canonical basis of C to the E0 as the vertices, right? So the class of a vertex is the class of the canonical generator of the canonical basis element corresponding to the vector B, to the vertex B, And I take, because E is finite, I can sum over all of them. And this is what I will call the 1 sub E. So it's a distinguished element in this Bauer-Franks group. Okay. So in this case, we say that E is unital. And it corresponds to the Leavitt path algebra being unital, and also to the sister algebra, the Kunz-Krieger algebra being unital. Okay. So we call E purely infinite simple if OE is purely infinite simple, which is equivalent to L, so which, if L is a field, is equivalent to LE being purely infinite simple, and it's also equivalent to E, so graph satisfying some graph conditions on it. Okay. So, okay. Yeah. And why do I care about the Bauer-Franks group? Well, so K0 of OE is the Bauer-Franks group. And this is also, if L is a field, or the integers, then this is also K0 of LE. In general, K0 of LE is K0 of L, tensor the Bauer-Franks group, at least for the most general ground rings L that we are going to consider today, which is L regular supercoherent. So the supercoherence is a special power that they have to, that allows them to have this formula to be true. This concept includes, I'm not going to define it, but includes all Noetherian regular rings. So for example, of course, it includes all fields and the integers. It also includes the rings of integers in any number field, and also the rings of functions on any affine algebra variety that is smooth over a field. Okay. So far, so good. And now I'm coming to, yeah. So one more thing is that K1 top. So when I say I put the superscript top, I mean that the topology of the sister algebra is taken into account. So it's the Banach algebra K theory. So K1 top of OE is free, it's a free abelian group of rank R, where R is the rank of the Bauer-Franks group. Okay, so if you know the Bauer-Franks group, you know K0 of OE and also K1 of OE. So you know the K theory. So the Bauer-Franks group determines the Banach algebra K theory of the Kunz-Krieger algebra. Okay. So now I come to state the known result And the problem that I want to tackle is all right. Yeah. So let me recall the Kuntz-Rordan theorem, which appeared in a paper by Rordan in the old K-theory journal in 1995. It says that if E and F are finite, so when I say that the graph is finite, I mean not just that the vertices are finitely many, but also that the edges are finitely many. So assume that E and F are finite and purely infinite simple, and say you have a group isomorphism which sends the distinguished element to the distinguished element. Then C left to an isomorphism of C star algebras OE to star isomorphism of C star algebras OE OF. If C is non-unital, so it doesn't send one-to-one, you still get Morita equivalence. So stable isomorphism. Okay. So this is now covered by the Kirchberg-Phillips theorem. Since they classifies nuclear separable unital purely infinite simple C-star algebras, since OE is always nuclear, and if it is finite, it is also unital and separable, and I'm asking that it be purely infinite simple. So why is this covered? Because here the isomorphism, I have it only at BF, at the level of B, of the Bauer-Franks group, which I said is K0. But since I said also that K1 is free with the same rank as the Bauer-Franks group, an isomorphism, so C induces an isomorphism between the C-star algebra K-theory of OE and that of OF. Yeah. So the algebraic Kirchberg-Phillips problem is find algebraic analog of Kirchberg-Phillips, or at least of Kuntz-Rordan. I mean, the right way to state it is find a class of purely infinite simple algebras which, and a set of of K-theoretic invariants that classify them. And this class should at least include the Leavitt path algebras for Leavitt path algebras. Okay, so this has been formulated as a question in a paper by Abrams and Lowley and Pardo in the Journal of Algebra, 2008. Okay. So my talk is about this problem, and I will first talk about what doesn't work or doesn't seem to work, and then I will leave the positive results for the end, like in a Hollywood movie that things go wrong until they begin to go well again. All right. So one approach to this problem is to use a theorem of Frank's. So yeah. So approach one, which I will call graph moves. Okay, so this theorem of Frank's published in Ergodic Theory and Dynamical Systems in '84, which says that for the purpose of this talk, we have E and F a finite and essential, and add purely infinite simple because it doesn't bother us. So that not only BFE is isomorphic to BFF, but also that the sign of the determinant of the matrix 1 minus AET is the same as the sign of the determinant of 1 minus AFT. So here I should say that under this hypothesis on E and F, the graphs are regular, so that these matrices are square matrices, and you can actually take the determinant. So the hypothesis in the Kuhn-Jordan theorem is only this: the Bowen-Frank group, Bowen-Frank groups are isomorphic. This implies that the determinants of these matrices have the same module, but they could have differing signs. If I additionally ask that the signs be equal, then Franz tells me that we can get from E to F via a finite sequence of specific moves, graph moves or alterations, or what you want to call them, of graph moves. And in a paper by theorem, in a paper by Abrams, Lowley, Pardo, and Smith, Journal of Algebra, 2011, they show that Frank's moves preserve the Morita class of the Leavitt path algebra. Okay, so you can move, if in addition to having this isomorphism, you would also know that the signs are the same, then you will be able to get from LE to LF via a finite sequence of moves that are Morita equivalencies. So you end up with LE and LF being Morita equivalent.
Are your algebras unital?
Yes, because E and F are finite. Yes.
What do you mean by finite?
That, as I said before, that both the vertices and the edges are finite sets.
Okay. So in particular, these are unital algebras.
These are unital algebras, indeed. Yes. Yes. I mean,
The reason I ask is it's not so clear what Morita equivalence means for algebras without unit.
yes, but there is a well-developed theory, championed among others by Abrams, for rings which have local units.
Oh yeah, local unit, fine. Yeah, for local units, still
And,
okay. But
yeah, and Leavitt path algebras.
If you have algebras which do not have local units, fine, that's fine. If you have an algebra which does not have local units, it is not clear what Morita equivalence should mean. In my opinion.
Yes, certainly, that's the widely held opinion. But Leavitt path algebras always have local units, no matter how infinite the graphs are.
Good. No, I completely agree with you. Local units, fine. Everything is fine. Yeah,
okay.
Good.
Okay. So, okay. So the problem that remains is, well, what can we do about the sign? And so, so to prove the Kunz-Jordan theorem, as done in the paper by Jordan, you need to use a trick developed by Kunz. So you need a further move called the Kunz splice. The Kunz splice, which I will now do a picture for you, is a move that doesn't change the Bauer-Franks group, but which does change the sign of this matrix. So, so you have your graph E here, and you construct a graph E minus, that's the Kunz splice of E, which takes some vertex in E, which lives in some cycle, and adds a picture like this. Then the effect is that, as I said, the Bauer-Franks group of E is isomorphic to the Bauer-Franks group of E minus, but the determinant of 1 minus AE minus T is minus the determinant of 1 minus AET. So the problem, if we want to prove Kunz-Jordan using some of the techniques developed in the original proof, we will need to show that the Kunz splice preserves the Morita class. So in a sense, we will not to know that the sign is somehow a Morita invariant of the class of the Leavitt path algebra. A key, in fact, the key case that is needed is that of a very simple graph. So, key case is when the graph E is R2. R2 is a graph with one vertex and two loops. So the arc comes from thinking that it's a rose with two petals. And so L over R2, I will call L2. And L of R2 minus, I will call L2 minus. And, well, what happens here is that the 1 minus A R2 is minus 1, and that the determinant of 1 minus A E minus T is 1. So they have different signs. But in any case, remember that the Bauer-Franks group is the cokernel. Here I can put the T, it doesn't matter because it's a 1 by 1 matrix. So remember that the Bauer-Franks group is the cokernel of this matrix. So the cokernel of minus 1 or of any isomorphism is 0. And the same here. So is there an isomorphism between 0 and 0? Of course. Does the isomorphism send the class of 1 to the class of 1? Of course, because they're all 0. And so if Kuhn-Jordan theorem were true for the Leavitt path algebras, since, by the way, this graph is purely infinite simple. And taking the Kuhn's splice preserves that. So this is still purely infinite simple. So if what we want, if the Kuhn-Jordan theorem were true algebraically, then L2 and L2 minus should be isomorphic. And whether this is true or not is open. However, the existing results around this problem that I know are mostly negative, are all negative. So what I mean, a negative result about the question that I just said that is open. Well, I mean that if you not only require that this be an isomorphism, but require additional conditions, then no such isomorphism exists. Or you require a specific, so here, the most interesting case is when we are doing this over the field of complex numbers. But you can also do it, say, over the integers, right? Or require additional conditions, require that, I will tell you what the conditions are.
Is the question whether,
this is what I'm going to say right now.
Is the question whether these two algebras are isomorphic, or is the question whether the two algebras are Morita equivalent? What is the question?
The question is whether they are isomorphic.
But
they are also not Morita equivalent. You can also ask whether a Morita equivalent, that is also open.
Oh, so both questions are open?
Yes.
Okay. Okay, good. Thank you.
You're welcome. Well, okay. So, negative results. And the first one is C-graded maps. Whenever you have any graph, be it finite, purely infinite, simple or not, you have a C grading determined by declaring that vertices have degree 0, edges have degree 1, and the start of an edge, often called a phantom, degree 1, often called a phantom edge, has degree -1. So this induces a grading, and you may ask whether an isomorphism between L2 and L2 minus exists that is homogeneous with respect to the grading. And yeah, so it is folklore that no isomorphisms, no graded isomorphisms exist. And so the idea is the following. So the graded isomorphism of the Leavitt path algebras implies shift equivalence, and shift equivalent graphs have the same, the determinant of the matrix of these matrices have the same sign in the shift equivalence class. This is you can find it in the Douglas Lynn book on the, symbolic dynamics. So that's it. There is no C graded isomorphism. Now, whenever you have a C graded algebra, you automatically have a C mod 2 graded algebra. By just the even part is the sum of the LEN with n even, and the same with n odd, you get LE odd. So you may ask whether there is an isomorphism that preserves, if not the entire C grading, what about the C mod 2 grading? And yeah. And for this, if the invariant to look at, say at least if L is C of the field, is the K theory of C mod 2C graded modules. So you take the projective, you look at the category of C mod 2C graded modules over LE, and look at what are the projective objects there, finitely generated projectives, and well, you take the Grothendieck group of that. This is the K the Grothendieck, I mean the graded K theory, and if you do that, you get what I call BF bar of E. So this is, so the bar here means is the Bauer-Franks module over the ring W, C of C. This is the group ring of C mod 2C. So I write sigma, I denote C mod 2C multiplicatively. So it has two elements, 1 and sigma. So the group algebra, the group ring is generated by sigma, and the result I call W. This is a ring. Sigma square is 1. Okay. And what is this? Well, so F bar of E is the cokernel of 1 minus sigma AET, where now I look at this as a matrix living in W E0 times reg E. Okay, so in other words, so what does the module? Why is this K0 graded K0 a module over the group ring on C mod 2? Because we have an action of C mod 2 in the category of graded C mod 2C graded modules, which takes a module P0 plus P1 to P1 plus P0. So you shift the gradient. This defines an action of C mod 2, and so the graded C mod 2C graded K0 of LE gives you a module over the group ring, which is W. And that's this module. And we have the following proposition. There is no unital C mod 2C graded homomorphism from L2 to L2 minus, nor for L2 minus to L2. There is none of this and none of this. Proof. If I do BF, I compute that this is C mod 3C, where the unit goes to the unit. And that BF bar over 2 minus is C mod 7. So, and also the 1 goes to 1. And so if there were a unital graded, C mod 2C graded homomorphism, then there would be a group homomorphism from here to here or in the opposite direction, mapping 1 to 1, so it wouldn't be 0. But there is no non-zero group homomorphism joining these two, so that's the proof. Done? Okay, so this is for what I have, the new thing I had to say about grading. Okay, the C mod 2C grading.
I have a question about your
yes.
algebras.
Yes, Paul.
These are just algebras. These are not C-star algebras, anything like that. These are just algebraic algebras.
Yes.
Are your algebras type 1 in the sense that if we have two irreducible representations with the same ideal, the ideal is the null space of the irreducible representation. If we have two representations with the same ideal, those irreducible representations are equivalent. This is usually called type 1. Is this true for your algebras?
I have no idea. I haven't never studied the representations, but of the Leavitt path algebra. But maybe I think at a certain point in time I saw that Gene Abrams, who wrote a book on Leavitt path algebras, was present in the public. Maybe he can answer that
Gene,
question.
he's still present. Gene, can you answer this question? He's still present. Okay.
Maybe he's present in spirit, but
yes.
Well, if you have
present too.
If you have an irreducible representation for one of your algebras,
yeah,
what is the range of that representation? What does it surject onto? An irreducible representation for one of your algebras. For example, does it surject onto all n by n matrices? Let's say we work over the top.
But wait a second. Our algebras are purely infinite simple, so they have no finite dimensional representation.
Okay, so what does it surject on? They have no finite dimensional representations.
Yeah.
So what is the image? What is the range of an irreducible representation for one of your algebras? Is it something like compact operators? Is it some non-closed version of compact operators?
Or I don't understand why you put this question, because if the algebra is simple, you cannot characterize anything by an ideal, because there is no ideal, so forget it.
No, but I think that what Paul is asking is about the left ideal, or something like this.
No, because in the type 1 case, you take the true ideal. You don't take the left ideal. So, I mean, that question has no, I mean, it has a trivial answer. The algebra is simple. That's it.
I think they're definitely not type 1.
These algebras do these algebras have irreducible representations?
Of course they do, but I mean, they are typically not type 1, you know, as Joachim says. I mean,
Okay.
we know these algebras very well. They are very far from the type 1 world.
Oh, I see. Okay. So these are very far from type 1. That's the answer to my question. All right.
Okay.
Right.
Sorry.
Okay, good.
Well, you see, I had a question answered by a Lincoln, so I cannot complain.
Well, Alain
Okay.
Kahn answered my question. Alain Kahn has answered many of my questions. And,
Okay,
and he continues
good,
to
very
do
good.
Okay.
Okay, so the next stop is what about star isomorphisms?
Mm.
So to talk about star isomorphisms, I first have to give my algebras a star, so an involution. So we begin with L, the ground ring with an involution. And you can extend it to LE via sending, well, I mean, V to V, E to E star, and E star to E. And the scalars, well, you just use the involution you had on L. Yeah, so for example, this, when L is the complex numbers, then the norm that you put on LE, whose completion is the Kunz-Krieger algebra, is a star norm with respect to this star, where the involution is complex conjugation. Okay, so of course, if the ring L is, say, the integers or the rational numbers, the only involution is the identity. And a theorem by Johansen and Sorensen, published in Journal of Pure and Applied Algebra 2016, said that there is no star isomorphism from L2 Z to L2 minus C. So the C between parentheses is not that C is a graph, but that I am taking my coefficients over the integers. So here L is C. This is what it means. C the integer. So there is no star isomorphism over the integers. But the big question is whether this can hold over the complex numbers with complex conjugation. Because after all, you know by Kunz-Jordan theorem that the algebras are isomorphic once you complete. And so the question is, were they isomorphic before? And this is star isomorphic before. And the star is the star with respect to complex conjugation. Okay, so here so this is a result, and what I have to say here is what so the same question with coefficients, the complex number is open, yeah, and say complex conjugation as involution. I'm not going to solve this, but I'm going to put a new involution on LE, which I call bar. So bar V is B, but bar E is minus E star. Minus E star. And of course, bar E star is minus E. Okay? So I just stuck a sign there. And okay. So, and the proposition is that there is no, so LE bar is LE with the involution bar. And the proposition is that there is no unital star homomorphism from L2 bar to L minus 2 bar, nor from L2 minus bar to L2 bar. Okay? Which you'll see that the statement is similar to the one we had before on C mod 2C graded things. What happens is that one can introduce an invariant that preserves, that is the appropriate invariant for algebras with involution, which in the particular case of the Leavitt path algebra, when you put this involution, you get the same group as when you consider LE as a C mod 2C graded algebra. So again, because there is no group homomorphism, non-zero group homomorphism from C mod 3 to C mod 7, you get this. And let me tell you what this invariant of the star algebras, of algebras with involution is, or more generally, of rings with involution. So if you come from C star algebras, well, I mean, then K0, you can compute, you can think of it as difference of classes of Murray von Neumann classes of idempotence, but also Murray von Neumann classes of self-adjoint idempotence, that is projection. Now, for a general ring with involution, those two things may be different. So K theory for star algebras. Okay, so say R is unital with an involution, then you may consider B of R star, which is the Murray von Neumann classes of self-adjoint idempotence in M infinity of R, where here M infinity of R is equipped, as you can imagine, with the transpose conjugate involution. Okay, so A star Ij is Ji star. Right. And then, well, you consider K0 bar star to be B of R star group completed. Right. So that's a group completion. And this gadget has not too many properties. But it does have one basic property. It is Morita invariant. So appropriately star Morita invariant. So in particular, so if you consider the inclusion element to R, that sense in the upper left-hand corner, and you consider this with this involution, then this induces an isomorphism. Okay? So this is iso. But the good theory is not this one, but you need, so here what you're doing in terms of projective modules with forms is you're considering all the projective modules equipped with Hermitian forms that correspond to orthogonal direct summands of the usual inner product. But there are more Hermitian, non-degenerate Hermitian forms than that, and you need to capture all of them, and you do this as follows. So you consider M plus or minus R, which is M2R with involution bar, so that bar of A, B, CD is A star, D star, so far the same as before, but here we put minus C star and minus B star. Okay, and then Hermitian K0 or bit Grothendieck group of R is K0 of M plus or minus R star. Okay, and so this same iota, this same map with the same formula, but consider now as a map to M plus or minus R, this induces a natural transformation but this is not usually an isomorphism. It is an isomorphism if you can write -1 as a sum of elements of this form. So if -1 is positive in R, then this is an isomorphism. In general, it is not. And what happens is this K0 of H is also K0, let me write it down here. K0H of R is also a W module. Sigma acts tensoring with iota plus, iota minus of 1, where iota minus from R to M plus or minus R sends A to the other corner. Okay. So these iota minus and iota plus are different in different maps here. Right. So what happens is you can compute lemma, say, if L is a field of characteristic not 2, then K0H of LE is K0H of L tensor W with BF bar of E. And if L is C with complex conjugation, so you take this and, well, so let me put C. If I write C for C with complex conjugation, then this is W. Okay, so when the ground ring is the field of complex numbers equivalent to complex conjugation, here these two cancel and I get BF bar of E. So how do I apply this to the non-existence of homomorphisms between L2 and L2 minus that preserve the funny involution bar? Sorry, I need a bar there. So, and here, you can also compute this. And this is this. With the usual involution, you get the Hermitian K-theory of L tensored over the integers with the Bauer-Franks group of E. But if you put this other involution, you get tensor product over W with the Bauer-Franks module. This one, for L2, this one is 0, but this one isn't. Okay? So that's why I need this funny involution to show that there is no unital involution preserving homomorphism for that funny involution, because I get this. Right. So how much time do I have? So the positive results seem I have to,
okay, you
to have the fewest. How many?
25 minutes.
25, okay, sure. Okay, so this is, so let me recap. We have started with the Kunz-Rordan theorem, tried to see whether we could prove a similar thing for Leavitt-Pass algebras, followed one approach starting with Frank's theorem, and using results of Abrams and collaborators, and we reached to the problem of whether the Kunz splice changes the isomorphism class or the Morita class, and it appears we don't know, but it looks like you don't have that isomorphism. But in fact, we really don't know. Okay. So another approach would be, well, let's do what what is involved in the proof of Kirchberg-Phillips, right? So let's go to the approach 2. Let's start with Kirchberg-Geneva theorems. So this says that if A is a Kirchberg algebra, which to me are unital, so unital, nuclear, separable, purely infinite simple, then if you do A tensor O2, you get O2, and if you do A tensor O infinity, you get O infinity. Okay?
Are these C star algebras? Are you talking about?
Yeah, the C star algebras. So
C star.
On is O of the graph with the rows with n petals, the graph with just one vertex and n cycles. Okay,
Hawaiian earring.
Sorry? A Hawaiian, well, yeah, well. Okay. Yeah, so this is the sister algebra tensor product. This is also sister algebra. But one question is, well, can we do the same thing algebraically? So that would be a second approach, but this approach ends easily because the answer is just no. So in a paper we have in the Proceedings of the American Mathematical Society, published in 2013 with Pera Ara. So say that you have E and F finite graphs, so that E and E having say purely infinite simple to be not to have to explain so much, but this will do. Then LE tensor LF. So here, say L is a field, and the tensor is over L, over this L, is not Morita equivalent to any Leavitt-Pass algebra. And the reason is simple. The global projected dimension of any Leavitt-Pass algebra is 1 or less. Whereas the global projected dimension of this is 2. So they cannot be Morita equivalent. So this approach, right from the start, you do not go anywhere.
But also graph sister algebras are not closed under the tensor product. You need to go to higher rank graphs, right?
Well, okay. But I mean, but if A were O2, then I mean, you have O2, tensor O2 is O2.
Yep.
And O infinity, tensor O infinity should be O infinity because they are purely infinite, simple, unital, and nuclear.
Yeah, that's a special
However,
case.
yeah.
Are
However, you do not
about-
get L2. Sorry? Finite, no. Finite, no. Unital. Unital. So finitely many vertices.
Are you talking about C-star algebras here? What algebras are you talking about?
So this one are star algebras, and this one are algebras.
The proposition, the lower part are not C-star algebras. They are just algebras.
No, because I call, so the way to tell whether I'm talking about sister algebras or about plain algebras is that sister algebras are O.
Yes, good.
Whereas plain algebras are L.
Yes, thank you. Okay.
You're welcome.
So what about what about the Piotr Hayat's comment? You should go to higher degree graphs, and then
I mean, but what I'm trying to negate. So but what I say is that this is not true, and that this is not true. So this shows that the analog of this isn't true, and this is all I care.
What is Piotr trying to say? What are you trying
Guillermo explained it. You see, what I was saying
Ln is L of Rn.
And in some particular cases, very special cases, when you have two graph sister algebras, they take their tensor product, and it's again a graph sister algebra. But it is for these special cases. And Guillermo is now trying to determine if it works for the same special cases, but without the completion on the purely algebraic level, right? So that's my comment was relevant, but of course, as Guillermo pointed out, this is I had a general quantifier, and he has just a very special case. But Paul, it's very helpful to think about the Leavitt path algebras as Hopf algebras for compact quantum groups. Yeah. You have the sister algebra of a compact quantum group, it's a sister algebra, but we have Peter-Weyl theory due to Voronovich, and then we have a very nice, dense star subalgebra, which happens to be a cosine-simple Hopf algebra. So inside, graph sister algebras, you have these beautiful Leavitt path algebras, which are dense subalgebras inside, but they are not complete. They are purely algebraic algebras, like Hopf algebras.
Well, this is what happens with compact Lie groups.
Yeah.
Or maybe, in fact, with compact groups in general, but in particular with compact Lie groups, this happens.
Yeah.
Right? You have within the C-star algebra, you have what you might call a purely algebraic algebra, which is a Hopf algebra.
Yeah. And here you have Leavitt, and this is very important. Okay. Sorry for this long.
No. Okay, fine. Okay. So let me go to the approach that does work. At least in part, okay? And this is a common argument in KP and Kunz-Rordam, in both the Kirchberg-Phillips theorem and the Kunz-Rordam theorem. So first, you show that if you have an isomorphism between BFE and BFF, then you can lift it to an invertible element, sigma hat, in Kasparov bivariant case theory of OE OF. Then you describe KK of OE of F as homomorphisms divided by homotopy, and also as homomorphisms homotopy, which I denote this way, and homomorphisms divided by approximate unitary equivalence, which I denote by 2 of these. And then finally, you use a theorem of Elliott, which appeared in Krell in 1993, which says that if you have unital sister algebras, you have these sister algebras, you have phi 0 and psi 0, so that phi 0 tensor psi 0 and psi 0 composed with phi 0 are both approximately unitary equivalent to the identity maps, then there exists phi and psi, so that actually phi psi is the identity, and so is psi phi. Okay? So this is a structure, more or less, grosso modo, is a structure of the proof in both cases. Now, for this part, I don't have any algebraic analog. I'm not saying it doesn't have one, but I mean, here it uses analysis, uses approximation. So one had to think, first of all, what can be meant for approximation in algebraic terms. But, so this I don't know. But this, the analog of this, does work. Okay? And so, let me tell you. So first of all, one needs to have some algebraic variant of bivariant K-theory, some algebraic variant of homotopy. So this I don't know, but I do have a description like this modulo algebraic homotopy. And using it, what I get not, so I get that an isomorphism between BFE and BFF for E and F finite pure infinite simple gives me a homotopy equivalence of the Leavitt path algebra. And I can I can also get that the equivalence is B star homomorphisms. And the homotopies preserve the star.
And this is for the usual star, not this funny one.
Well, for the usual star, and for the funny one, I have partial results, but yeah. So I'm also interested in the funny one, but the main results are for the usual. So the basic, so by homotopy, so you have two homomorphisms, F0 and F1, and then, well, you can imagine a picture like this, where here you have B of T. So this means, so F0 and F1 are homomorphisms from A to B, they and B are algebras, and we say that they are elementarily homotopy. If there is a homomorphism from A to BT, so that when you compose with evaluation at 0 and L1, you get F0 and F1. This is a symmetric reflexive relation, but it is not transitive. So, because the usual thing that you do to make usual homotopy transitive is you split the interval into two, and you can, that's not an algebraic operation, but you take the so homotopic, you take the transitive whole. So this means that you can go from F0 to G in a finite number of steps, so that at each step you have an elementary homotopic. And then you may add a star here if F0 and F1 or F and G are star homomorphisms, and all these H's that appear are also star homomorphisms. So you add stars everywhere. Okay. Okay. And then I need to put this together with stabilization. So say you go from A to B, and here you compose with iota 1 to M2 B. So you can do this, and we say that F is M2 homotopic to G if iota 1 composed with F is homotopic to iota 1 composed with G. And again, you can put stars if these two are star homomorphisms and the involution homotopy is star involution preserving. And finally, you can go from here y plus to M plus minus M2 R B. And if this is M plus 1 minus 2 G homotopic, and this is always a star homotopic, if I plus I1 F is homotopic to I plus I1 G. Okay. So let me state the theorem. Right. So okay, I have so I have for all so I have a theorem for joined with Diego Montero. So yes. Which is not involution preserving classification of Leavitt path, purely infinite simple Leavitt path algebras. But since I have little time, I will only state the new one. And so this is, I have a result that is for any ground ring that is regular supercoherent. But it's easier to state if I assume that -1 is positive in L. So don't dismiss this just because -1 positive is something that, you know, far-fetched. But this is true when L is the complex numbers with the identity as involution. But I also have a theorem for even without assuming this. So we have L regular supercoherent. With 2 invertible in L, -1 is positive in L. And we have that VFE is isomorphic to VFF. Then there exists phi from LE to LF psi from LF to LE, star homomorphisms, so that phi composed with phi is n plus minus 2 homotopic to the identity, and the same with phi composed with psi. And this one, you can take them to be full. In fact, to have satisfy a strong fullness condition, if you drop this assumption, then you get a similar thing, but now the maps do not go to the Leavitt path algebra, but go to matrices on it. And you get that, say, for example, this composition. So you cannot compose these two, but you can take n plus minus of this. And then what you get is n plus minus 2 homotopic to the composite of twice this inclusion. And yeah, and this is a stable homotopic to this. Okay, so that's it. These are the results. So as I said, the results similar to this for morphisms that do not necessarily preserve the involution. And in that case, you do not get n plus minus 2, but just n2. So n plus minus 2, you stabilize twice. So you end up with 4x4 matrices. Right? They become homotopic after embedding it in these 4x4 matrices with this one involution. And in the case when you do not insist that the homotopy be involution preserving, you can get down to M2 equivalence. And if you additionally have 1 goes to 1, then you get actual homotopy without M2, at least in the non-involution preserving classification. So I suppose that my time is up.
This is why I marked our seminars as not appropriate for children. Because if any child would see -1 greater or equal than 0, this would be quite confusing.
Yeah, well, but here I dropped it. Yeah.
Ah, you drop it. Ah.
So if -1, so the difference is, so if I have this hypothesis, then my homotopic equivalence go from LE to LF and NF to LE.
Mm-hmm.
If I no longer require this, then instead of having LE go to LF, it goes to 2x2 matrices over LF. And the same in the opposite direction.
Okay, I misread this drop. I read it as prop.
Ah, no.
Okay, anyway, like in the Hollywood movie, you ended on a positive note, just a minute ahead of time. So thank you very much. Let me find this icon with clapping hand. Yes. Okay. Yes. So thank you very much. And now we begin with questions. So please fire at will. I mean, whoever wants to ask a question, go ahead. Joachim, you seem to be very willing to ask a question. Go ahead.
I have a comment on this. My coworkers in the representation theory of p-adic groups and we have been thinking about this kind of thing, except in a parallel universe to your universe. Now, one of my birthdays, I have a lot of birthdays, I know, but one of my birthdays, I think, was 80, my 80th birthday. So Piotr's Institute there, they published a special edition of their journal for my birthday. I urge you to read my paper with my coworkers. My coworkers are Anne-Marie Aubert, Raja Plyman, and Martin Soloveld. What we did, what is your journal called, Piotr?
It's Banach Center Publications.
Yeah, Banach Center Publications for when I was 80. Okay, wonderful. We introduced for our class of algebras that we were interested in, we introduced a weakening of Morita equivalence. That is, if two algebras are Morita equivalent, they are equivalent in our new equivalence relation, but as happened in the representation theory of these algebras introduced by Bernstein, those algebras are not Morita equivalent, but they are equivalent in the new equivalence relation. So if you will allow, I would like to make a prediction, if I may. If you adapt our definition to your class of algebras, this will take some work. This will take some thinking. It is my opinion, of course, I could be wrong, I mean, obviously, but it is my opinion that if you adapt our definition, it's a weakening of Morita equivalence. It makes it easier for two algebras to be equivalent. You will find that these two algebras you are interested in, if you adapt our definition to your class of algebras, you will find that these algebras are not Morita equivalent, but they are equivalent in the new equivalence relation. The point is that with our class of algebras, there were algebras introduced by Bernstein. These are affine Hecke algebras, for example. These are well-known algebras. These are wonderful algebras. And these algebras, they look like they should be Morita equivalent, but they are not Morita equivalent, but they are equivalent in the new equivalence relation that we introduced. So I turn you to Piotr. Piotr, please give him the reference. It's what, Banach Center Publications? What is it?
Volume number 120, if I remember correctly.
Yeah. Banach Center Publications?
Yeah, volume 120 is just was published. It's at the top. If you go to the Banach Center Publications, I mean, right now, I think we have volume 123, so this is not very deep down.
Yeah, so it's my co-workers, Anne-Marie Aubert, she's French, Roger Plyman, he's British, and Martin Soloveld, he's from Netherlands. And then there's me. I, alas, am American. So this took us many, many years to formalize this. I mean, we could see what was happening. You would think that these algebras should be Morita equivalent. And you do this, you do that, and somehow they don't quite become Morita equivalent. You could never prove somehow that they are Morita equivalent. But it turns out they are equivalent in the new equivalence. Oh, all right, okay, thank you very much for this interesting talk. You have a very interesting sort of concrete problem. It's yes or no. Okay, thank you.
I think Yahim wants to ask a question. Yahim, please go ahead.
Yeah, can I make a comment on the talk?
Sure.
Yeah, well, you talked about analogs of the Kirchberg-Phillips theorem and the Kunz-Rödam theorem. Well, they tell you that two graph system algebras, OE and OF, are isomorphic if and only if the Bowen-Franks invariants are isomorphic. But you can also ask, but then you had the result about homotopy equivalence. You can also ask the question about homotopy equivalence for the graph system algebras. And that's a much easier question. And there is a much older paper by myself, I mean, much older than the Kunz-Rödam or Kirchberg-Phillips. If I'm not mistaken, I show that two of the graph system algebras are homotopy equivalent if and only if the Bowen-Franks invariants are isomorphic. And that's
you mean the one about the homotopy groups or the endomorphisms?
Yeah, yeah. I think it should be a consequence of that. I mean, in this paper, I analyze the homotopy groups of the endomorphisms of a graph algebra, but you have homomorphisms from one to the other and back, and then you compose, and then there are explicit criteria for when these are homotopic to the identity. I mean, it's just...
That's a good point.
I mean, that's really, for these algebras, it's much easier than you don't need asymptotic unitary equivalence or such things. And
Okay.
Okay. Any further questions or comments?
If I could ask, I would like to ask whether is there a definition of higher K groups for this Hermitian theory?
Yes. 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 So this is also quite old.
Wasn't this developed by Karoubi? Doesn't this go back to?
Yeah. Yeah. Exactly. So.
It's periodic. I mean, it's you have the whole package.
No. The periodic ones are the. Okay. So there is a difference between bit Grothendieck groups, which are not periodic, and bit groups, which are kind of periodic.
Okay, good.
But so you take so you are so KL, I mean Kn for n bigger or equal than 1 of the ring R, unitary ring R, is the homotopy of BGLR plus construction, right? So this, you may be used to this, right? And what KNH of R is pi n of B U R, well, so you, yeah. So you could do this. Star, you could define it, well, no, not star, no. So, so let me see. So let's write O. UH of R for the unitary group, infinite unitary group of n plus 2 minus of R. So here you take the unitary matrices over this ring with involution of finite size, arbitrarily large. And then you take B of U, H, R, take the plus construction, take homotopy groups. This is Hermitian KH. There are several definitions, but this is the one I consider. And I use a bivariant version of this, a homotopy, polynomially homotopy invariant, bivariant version of this theory that we introduced in a paper with Santiago Vega. So this is KKH that you can find in the archive from last year. So this is a bivariant version.
Okay, thank you. Thank you.
Anybody else? Questions or comments?
Yes. For your class of algebras that you are studying, Morita equivalence can be defined in terms of a pair of bimodules. Okay, it's a very algebraic definition.
I like to think of it as full corners.
Okay. Or you can define it that the categories of modules are equivalent as categories.
Mm-hmm.
Yeah, this would be Morita equivalence without taking into account the involution.
Yes, I see. Okay, but you want to take into account the involution. Okay, all right, good. Okay. So, I mean, for your class of algebras, so these are these graph algebras, is Moridi equivalence defined in terms of bimodules? Is that the same as saying that the category of modules, that these are equivalent categories? It is the same thing. Okay.
At least if you do not take into account involution. If you do, I suppose, I think there are some old papers to that effect. But since I think of idempotence and projections and such things more than modules.
Okay.
All right.
Okay, good. Thank you.
Anybody else? Richard, Tomek, Jean?
Yes, I have a question.
Yeah.
Go ahead.
I have a question. When you are comparing this Hermitian K-theory and this Z2-graded one, what is this based on? Where are these Hermitian forms in this story?
Well, I mean, let me see if I understand you correctly. So here, if you want to think in terms of categories, so you take all projects, so pi, p, phi. Okay, so you need, wait a second, you need, let me see, you have a module P, and then you have P star, which are all the alpha from, so P is a module over R, and these are alpha from P to R, which satisfy that alpha XA is A star alpha X. So this will be like the Hermitian dual. And then you have a P together with an isomorphism. So this is a module over the same side as P.
I know what is Hermitian.
No. Okay, but wait a second. So if you take all of this with P projective and finitely generated. Okay, and so this is a Hermitian category. It has a K-theory, and this K-theory is the K-theory, the Hermitian K-theory I talked about. So I don't think in terms of modules and Hermitian forms or anything like that. I think of rings with involution, right? And to me, what this means is that you have to take all projections. So any such P is a direct summand. So this is the standard theorem that the orthogonal direct sum of these two is the Hermitian module. So it's the hyperbolic modulon P, which is P plus P dual, equipped with the form that switches something like this. Yeah, well, yeah, with this form. And using that, if you have that twist invertible and so on, this is again an orthogonal direct summand of R to some n equipped with to some even n equipped with the identity minus identity. Right? So the endomorphisms of such a module with this form, so this form induces an involution on the endomorphisms. So in M2n of R, you have an involution that corresponds to the joint operator with respect to this form. And this involution is the involution with the sign. In the case when n is 1, it gives you this n plus minus. Right? So it's the involution that the usual involution, but with this sign. And so when you equip this is m plus minus 2n with the involution coming from the adjoint with respect to this. So all the forms, all the Hermitian, non-degenerate Hermitian forms over R can be seen as usual forms in, so-called of the ones that direct summands or orthogonal direct summands of the usual inner product, but not over R, but over the ring n plus 2, n plus minus of R. So I need to talk about projections and such things, because if you are in the business of lifting, so you have a homomorphism between the Bau and Franz groups. And then these Bau and Franz groups represent classes of projections, and you want to think, so the whole Hermitian K-theory are projections that have coefficients in m plus minus of R. And if R is purely infinite, simple, blah, 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 you do not need the n. You can reduce to n equals 1. Okay, so this is where the n, if the minus 1 is positive, then this Hermitian K-theory is the K0 star. So you can talk, you can talk about projections in R. Otherwise, if minus 1 is not positive, you need to use projections with coefficients in m plus minus R.
Mm-hmm. So essentially you are expanding your ring by Morita equivalence, and you are inducing new involutions using Hermitian forms.
Yeah, using the hyperbolic. So in the C-star algebra setting, the model involution, everything is modeled on this form. Everything is modeled on this form, and so the whole theory is based on the form that positive. So first of all, that elements of this form are positive, and moreover, that any element of this form in the C-star algebra can be written as a single y times y star, right? Mm-hmm. But here, my archetypal form is this. So it's a 2m by 2m form, which incorporates negativity. So this is my basic form.
Okay, not positive definite, in a sense.
Not positive definite. It's the hyperbolic form, and I take projections that represent direct summands of the free module equipped with this form, orthogonal direct summands of the free module equipped with that form.
So in the Witt group, it would be a trivial element. It would be a metabolic form.
Yes, this is yes, but not necessarily. Yeah, but in the free case,
this can induce a non-trivial involution on matricial idempotents.
Yes, because this is also. The fact that the Witt group is a group is related to the fact that if you have a module with a form, then you can add another module with a form so that the sum is hyperbolic. Mm-hmm. So, what I'm saying is that every module is a direct summand of the hyperbolic module. So that's, in that sense, it's the cofinal form, right? When I began thinking about this classification, taking involution into account, I thought, well, if I can classify up to not involution preserving homotopy, and this lives in K theory. So perhaps the abstraction for finding homomorphisms that do preserve the involution must live in the difference between algebraic K theory and Hermitian K theory, which essentially is the bit groups. But this intuition was wrong.
No.
Okay, thank you.
Bit groups do not get used.
Okay, anybody else? Richard?
I think Joachim wants to say something. Oh.
Joachim has his hand
Yeah, has his hands raised.
But
Yeah,
go ahead, Joachim,
comment.
if you want to say something, please do.
I made my comment before.
Okay,
Yeah, okay.
so you are happy. Okay, good.
Okay, I do have a question. So,
Go ahead.
Richard.
so the abstraction is this determinant, right? Signature of a determinant.
Yeah.
So what in some sense what you do is get rid of this abstraction. -1 is positive. Whether in your ring or whether you go to your 2x2 matrices with different involution, that's what you do, right? Essentially.
Not exact. No, because so there is so
That was not my question.
-1.
Go on.
Oh, okay.
No, that's not my question, right? Because it's a different story. No, my question is slightly different. So the way you don't see this the term if you play with C-star algebras, you don't see the sign. If you start to play with kind of smooth versions of C-star algebras, then the sign shows up in pairing between K theory and cyclic theory. Okay, so you see it directly.
I didn't know that.
Okay, you don't. You don't see it in O2, of course, because it's purely infinite. Still, somewhere this abstraction should show up in some version of pairing between K theory and cyclic theory. At least certainly that's what's happening if you do, say, non-commutative torus, for example. So if you take this non-commutative torus, right, then the C-star algebra cross product is invariant and the change of sign, so the determinant is not. So the invariant group is GL2, while if you look at the smooth part, it's SL2. And you see the difference when you pair cyclic theory to K theory. That's where you see the sign.
Well,
But I believe
but I know about this sign because there are signs that
sure, but it's the same sign.
Signs are there in the group.
But there's this kind of sign, right?
Yeah, but so one little thing. You do see the sign of the determinant if you take into account, as I said, the C grading. There you do see.
Yeah, but that's not that's much too coarse.
But it's the same as taking
it should be much
account...
coarser than Z grading, right? Z grading basically has the structure of Z grading keeps the structure of your graph, right? Essentially, Z grading sees the graph.
It is so. It is an open question whether the graded K0 is a complete invariant for the graded Morita class of Leavitt path algebras.
Yeah, okay, but sure, but still, it's in some sense. Well, if you look at the gauge group and Z grade, you get right, then you basically see your graph, right? So Z grading has a lot of information, has a lot of geometric information, which is far away from the algebra itself. So that's why it's not surprising that if you take Z grading or in Z-mod2 grading, right, then you can find some invariants which immediately see the difference. But somehow, in my experience, for difference between C-star algebras and the smooth versions is that you start seeing the signs of this kind of thing when you start pairing. So difference between GL2 invariants and SL2 invariants shows up when you start looking at the pairing between cyclic homology, which requires you to choose some smooth subalgebra,
but
and K theory.
what happens often here is that, well, first of all, K-theory of L2 and of L2 minus are 0.
Yeah, I know, but that's what I was saying. So this is.
Yeah, and often
but the
they are
invariant is
torsion.
still hidden somewhere, right?
But yeah, but and also they are often torsion groups.
Sure.
And cyclic homology groups, if you take them over,
You know that
numbers,
there are cyclic homology versions for in characteristic P. You know that, right?
You mean TC?
TC is almost overkill. But the stuff you did with Joachim, for example, and with Ralph.
Yeah, no, but this is torsion free, and so
no. Well, you leave that's when you leave you do characteristic P, right?
Yeah, I know, but we leave to characteristic 0 and tensor with a field. So
but you start with something with characteristic, I don't know, P, right? So of course not the original one's not torsion free. Original one obviously has torsion.
No,
right?
But
when you construct something, you construct something torsion free afterwards, right?
No, we construct something torsion free. But in any case, here the problem is not that the torsion is in the ground ring.
No,
but
of course not.
In the Bauer-Franz group, no matter if you take your algebra over the complex numbers, you may have torsion. It's often the case that there is torsion.
Well, then do TC. If you okay, then do TC. Okay. No, then do TC, but you don't have a problem there, right? But by somehow questions what is the invariant? That's basically what I'm asking. Because yes, you are right. That in some sense, K theory is trivial, right? If you take out 2 K theory is trivial. But still,
the pairing between K theory and something that is a divisible group will give you 0.
Well, it doesn't have to be divisible. Take TC, right? Just take TC for that matter. I don't know. I don't have an answer. Okay, I don't have an answer. I'm just asking, right?
Yeah, I have no idea about this.
Right. I'm just saying that my feeling is that at least in non-zero characteristic, it's very often this determinant shows up precisely in this pairing. Where there's a difference, there is kind of non-equilibrium between K theory, which would be topological, and cyclic theory, which requires you to choose some smooth algebra version. And that's where you see these determinants. It was just a question. I don't have an answer.
Okay. So to think about.
Good. Anything else? Anybody else? I go through the list. I don't see any raised hands. So in this case,
Joachim.
Joachim, he's clapping. Again. He's clapping. Yes.
Clapping. Okay.
Okay.
Clapping.
Okay.
I'm also clapping. Yes.
Wait.
So thank you very much.
Are you clapping, Joachim?
Yeah. Yeah, he was. So thank you very much for an exciting talk. And I think it worked pretty well with your whiteboard. I think it was visible. And but this time we'll have no slides available from your talk. But maybe
you can, recording.
Recording will be on YouTube. But maybe you can tell me which paper of yours or bunch of papers of yours are most relevant, and I will link them instead of your.
Yeah. Well, so the so I can send you. So it's the most relevant is the new paper that they have in the archive from this year.
Okay.
But I can send you the
no, that's
number
okay.
if you need it.
I can find it if it's on archive. I'll find it. So thank you very much, and let me say that we have a talk as well next week on 7th of April, and it's going to be Andrzej Sitasz, and if it's Andrzej Sitasz, it must be on spectral triples. So I don't remember the title, but it's Andrzej Sitasz.
Must be.
Must be. So for the time being, really, thank you very much. Thank you all for attending. Thank you, Guillermo, for delivering the talk. And I hope to see you guys next week. For the time being, I stop the recording and we adjourn. Thank you.
Okay. Bye. Bye.
Bye.